Welcome back everyone. This is Muhammad Rakibul Hassan with a new lecture on Electrical Circuits 2 course. So today's lecture is mostly focused on magnetically coupled circuits on basically transformer. So let's start. So first of all, inductance. So whenever we heard the name inductance, the first thing appears in our mind just like this. So it has some coil. So the coil could have n number of turns and the length is L, and the area where this coils is placed is the area has, let's say, A. Then we can say the inductance is basically according to this formula, where mu is the permeability. We know the magnetic permeability, so it depends on the material. So let's say this is a iron or ferrite core, so it should have some the relative permeability, which is mu suffix r, and then we can write the mu equal to basically mu suffix r multiplied by mu suffix 0, which is the permeability at air medium, 4 pi into 10 to the power minus 7. Anyway, so from this formula we can calculate the inductance value, where mu is the permeability, n is the number of turns here, number of turns in this inductor coil, and A is the area in meter square. So the area of that particular core where this coil is placed on in meter square, and L is the length of this particular coil, and finally we will get the inductance value in terms of Henry, the unit of inductance. And now we can say also this inductance is associated with a change in current, the change found in the flux density. So we can write the change in flux density with respect to change in its current. So let's say this is the coil through where we are giving a current of IL, and then definitely whenever we will changing the current, the flux will also be changed. So this is associated with the inductance value L. So this is a new formula, L equal to N d phi of DIL. Moving on. So now a very important formula in electrical history, I can say, Faraday's laws of electromagnetic induction. So this is a widely used formula, and it is behind many electrical devices, for example transformer, generator. So don't worry about these devices. If you don't know right now, you will surely read this in upper level courses. So anyway, Faraday's laws of electromagnetic induction state that whenever there is a conductor placed in a magnetic field, so then if there is a relative motion between this magnetic field, this is like this magnetic field from north pole to south pole, and the conductor, so whenever there is a relative motion between these two, a voltage will be induced across the conductor. So this is basically the Faraday's laws of electromagnetic induction. So if we say for example we have n turns of coil is placed on a magnetic field and there is a relative motion, then the induced voltage according to Faraday's law is E equal to N d phi of dt. That means the change of flux with respect to time. So the unit is definitely volt, since we are talking about induced voltage. And another term is we can say this is due to self inductance. So why self inductance? Because the magnetic field is associated with it here. Anyway, moving on. So now if we rewrite it in terms of inductance value, the self inductance value that I was talking about. So first of all, this N d phi by dt, I can change it with d phi of DIL. So since I introduced additional term, I need to multiply it with DIL in the numerator so that they can cancel out, and then the previous term dt. So now this particular portion n d phi of dIL, previously in our previous slide we mentioned it the L, basically the self inductance. So EL equal to L dIL of dt. So this is basically the induced voltage due to the inductance. More specifically, it is due to self-inductance. Now this formula, I think it is quite common to you, so probably you already used in Kirchhoff's voltage law. So let's say we have a circuit where we have a resistance, then inductance, capacitance. So whenever we want to write a KVL, and then we can write, probably you already wrote it in previous classes, or if not you will learn it. So anyway, you probably wrote it like Ri plus L di of dt differential equation. So probably you already studied, or if not you will study, don't worry. And for capacitance it is 1 over C integration of I dt. So these are the voltages, because I am talking about a KVL equation. So anyway, this term basically came from Faraday's laws of electromagnetic induction. Now, so let's focus on mutual inductance. So mutual inductance, basically the name mutual, so it exists between coils of the same or different dimensions. So self inductance is basically for a particular coil. So here is a magnetic field for which a voltage will be induced. So this is called self inductance. But when there are multiple inductance coil, then this magnetic field of one coil will cut another, so definitely there is another voltage will be induced, and this is called mutual inductance. And this particular concept is being used in transformer, and transformer is an electrical device, and it is used today in almost every field of electrical engineering and also in electronic engineering as well. So since you are going to be an electrical engineer or an electronics engineer, so definitely this transformer will be used in many of your devices and components or systems. So now let's watch a transformer. So a transformer, let's say since we are talking about a transformer, it has two coils. So let's say this is one coil through where we are supplying a AC supply. So this is denoted by VG. Since we are supplying an AC supply, so there will be magnetic field will be introduced here. So this particular magnetic field will be cut by the second coil, and we know that magnetic field is being cut in a conductor, so definitely there is some voltage will be induced, E suffix S. So this is the particular concept behind the transformer. So we are supplying voltage here, and through electromagnetic induction we are getting voltage in the second terminal. So here it is called primary, because the source is connected to this end, and generally we connect the load to this end. So this is called the secondary, or where we will get the voltages. So that's why this is denoted as secondary. Let's say the inductance, self inductance is L suffix S, and N suffix S is the number of turn in the second coil. And then in our first primary coil, let's say we have L suffix P is the self inductance of our first coil, that is the inductance value, and N suffix P is the self inductance, and IP refers to the current through the primary, and EP refers to the voltage across this terminal. So this is basically the transformer, and this is written here. So all I just mentioned, so it has two coils placed so that changing flux developed by one links the another. So the flux developed in our primary coil links the secondary coil, and this results in an induced voltage across each coil. Okay. So I already mentioned that the primary is where we will supply the source, and the secondary where we generally connect the loads. Now for the primary of the transformer, definitely we can say, according to Faraday's laws of electromagnetic induction, we just derived this equation. So previously we wrote it E equal to N d phi of dt. Now we are talking about particularly primary. So E suffix P equal to N suffix P equal to d phi P. That is the flux in our primary, phi suffix P divided by dt. So this is the induced voltage. And similarly, now we know that EP equal to L di by dt. Previously I already show you that I wrote it like E equal to L di by dt. So now if I replace, so it will be EP and then LP dIP. So that's the changes here. Moving on. Now similarly, this for secondary we can write it like previously it was E equal to N d phi of dt. So now we are talking about secondary, so ES NS. Now what will be the phi? So if we remember, phi p was generated in our primary side and phi m is basically the shared portion. So if I show you again, so let me clear all drawing. So if you notice here, phi p refers to this flux for this particular primary section. So flux is associated like here and here in all direction, and some portion is being cut in the secondary. We are calling it mutual flux. That means this is the shared flux and shared from the primary coil. So since we are writing the ES, so definitely we will write d phi m of dt, and since it is secondary, so ES equal to NS. Now moving on, so we are probably here. So this is the equation for voltage induced across the secondary. Now if all the flux links the primary and secondary are equal, that means let's say this is a very efficient system. That means all the flux produced in primary are shared with this secondary, then we can write phi m equal to phi p. Then this particular equation we can change it like this. So this phi m is changed to phi p. Now this is the equation. So now another new term which we call the coefficient of coupling. So coupling coefficient basically refers how good the coupling, or how good the combination. So what amount of flux induced, what amount of flux offered by primary is associated with the secondary is called the coefficient of coupling. So it is basically phi m divided by phi p. So we know that phi m is basically the shared portion from phi p. So this could be as high as maximum phi p. So phi p is shared, and what is amount of share is given or is found in secondary, we call it phi m. So that's why this shared portion can get maximum to phi p. So this ratio phi m to phi p, we call it coefficient of coupling, or small k. So we can understand that this could be greater maximum, this could be 1, so this can't be greater than 1. So this is written here. So coefficient of coupling, I just derived it.